everything is falling, right now. The Earth, the Moon, even distant galaxies all moving under the same invisible influence. Gravity never turns off, it shapes space, slows time, and hides mysteries we still don't fully understand. Stay with this journey, and don't forget to like and subscribe for more slow, thoughtful documentaries like this. Across the largest distances that can be observed, gravity appears as a quiet organizer of matter, shaping patterns that unfold over immense spans of space and time. The view begins far beyond any single galaxy, where clusters of galaxies gather into loose groups, and those groups stretch into long chains that span millions of light years. Each galaxy is itself a vast system of stars, gas, and dust. Yet here they become small points in a larger arrangement, drawn together by a force that acts across every distance without fading to zero. Observations indicate that these clusters move slowly relative to one another, guided by a shared attraction that arises from their combined mass. It remains uncertain whether all of the mass responsible for this motion is directly visible, since measurements suggest the presence of additional unseen matter that contributes to the overall pull. In this distant region, gravity does not act as a sudden force but as a gradual shaping influence. Galaxies drift through space with steady motion, their paths bending gently as they respond to the presence of nearby mass. Over time, these paths lead to encounters and mergers where two galaxies approach, distort, and eventually combine into a single larger structure. The process unfolds over billions of years, far beyond the span of human observation. Yet its effects are recorded in the shapes of galaxies that appear stretched, twisted, or surrounded by faint streams of stars. These forms provide evidence that gravity is not only holding systems together, but also transforming them continuously. The scale of this region makes gravity seem both powerful and subtle at once. The distances between galaxies are so large that the immediate effect of attraction appears weak, yet given enough time, even a small acceleration changes motion in a lasting way. A galaxy that begins with a slight inward drift toward a cluster will continue to move inward, its path slowly curving more strongly as it approaches regions of higher mass concentration. In this way, gravity builds structure step by step, guiding matter into increasingly organized forms without any abrupt boundary or edge. Light from these distant systems travels for millions or billions of years before reaching observation instruments. As it passes near massive clusters, the path of the light bends slightly, a phenomenon known as gravitational lensing. This bending occurs because gravity influences not only matter, but also the path that light follows through space. Observations indicate that the amount of bending can be used to estimate the mass of a cluster, including any mass that does not emit light. It remains uncertain how this unseen mass is distributed in detail, but its presence is inferred consistently through its gravitational effects. Within this wide region, gravity also competes with another large-scale influence, the expansion of the universe. Space itself is observed to expand, causing distant galaxies to move away from one another over time. In regions where matter is sparse, this expansion dominates, and galaxies drift apart. In regions where matter is dense, gravity can overcome the expansion locally, drawing galaxies together into clusters and groups. The balance between these effects determines whether a given region grows more spread out or becomes more tightly bound. The patterns formed by this balance appear as a vast network, often described as a cosmic web. Long filaments of galaxies connect dense clusters, while large empty regions known as voids contain relatively little matter. Gravity acts along these filaments, guiding matter inward toward the denser nodes where clusters reside. The motion is slow and continuous, with no sudden transitions, only gradual changes in direction and speed as matter responds to the surrounding distribution of mass. Despite the calm appearance of this structure, the underlying process carries a certain weight of inevitability. Gravity does not switch off, and it does not weaken with time in any local sense. Once matter begins to gather, it continues to gather, unless countered by other influences. This persistence means that small differences in density in the early universe grow over time, leading to the large structures observed today. Observations indicate that regions that were slightly denser in the past have become the clusters and filaments now visible, while less dense regions have become the wide voids between them. At this outermost scale, gravity reveals itself not as a simple pull between objects, but as a shaping principle that operates across the entire observable universe. It links distant systems through a shared influence that extends without clear limit, guiding motion in a way that appears smooth and continuous. The paths of galaxies, the bending of light, and the formation of large-scale structures all reflect the same underlying effect. It remains uncertain whether this description is complete. While current observations and theories describe gravity with high accuracy across these scales, questions remain about the exact nature of the unseen mass and the full relationship between gravity and the expansion of space. What is known is that gravity governs the arrangement of matter across the largest distances that can be studied, creating a universe that is neither random nor fixed, but slowly evolving under a constant and universal influence. In this distant region, the effect of gravity can feel distant and abstract, yet it sets the stage for every smaller structure that follows. The clusters, filaments, and voids formed here provide the framework within which galaxies, stars, and planets exist. The same force that guides these vast motions continues inward, shaping each smaller region in turn, always present, always acting, and always drawing matter into relation with other matter across the expanse of space. Within the broad pattern of the cosmic web, gravity becomes clearer as the force that gathers matter along extended paths rather than into isolated points. The largest empty regions remain wide and faint, while the denser borders between them hold chains of galaxies, gas, and dark matter. These borders form filaments, long structures that stretch through space like slow rivers of mass. Each filament contains many galaxies, but its full shape is not defined by starlight alone. Observations indicate that most of the gravitational structure is traced by matter that does not shine, while visible galaxies mark only the brighter portions of a deeper arrangement. The web is not a solid object, and it has no hard surface. It is a pattern created by motion, density, and time. In the early universe, matter is distributed with small differences from place to place. Some regions contain slightly more mass than others. Gravity strengthens these differences. A region with more mass pulls more strongly on nearby matter, and the added matter increases the pull further. Over billions of years. This slow growth changes a nearly even distribution into a network of dense strands and wide spaces. The process is gradual, but its result is immense. Inside a filament, galaxies do not simply rest in place. They move along paths shaped by the combined pull of surrounding matter. Some drift toward denser knots where clusters form. Others remain in looser groups, bound within the filament but not yet gathered into a cluster. Their motion is not random in the ordinary sense because each path carries the history of nearby gravitational influence. A galaxy's direction, speed, An eventual meeting with other galaxies depend on the mass around it and the way that mass changes over time. Gas also follows the structure of the web. Much of this gas is thin and difficult to detect. Spread between galaxies at very low density, it can be warm or hot, depending on how it has fallen into gravitational wells and how it has been heated by shocks and radiation. A gravitational well is a region where mass creates a tendency for other matter to move inward, like a depression in the motion of space. As gas falls toward denser areas, it gains speed, compresses, and heats. This heating can leave the gas too faint to see directly with ordinary light. Yet observations at other wavelengths indicate that it helps fill the spaces between galaxies. Gravity in the web acts without selecting one kind of matter over another. Stars, gas, dust, planets, and dark matter all respond to the presence of mass. Light follows curved paths through the same gravitational landscape. The result is a structure that can be studied in several ways at once. Galaxy positions reveal the bright pattern. Motions reveal the pull. Gravitational lensing reveals the mass, including matter that cannot be seen. Together, these methods show that the visible web is only part of the full web. The spaces between filaments, known as voids, are not perfectly empty. They contain some galaxies and gas, but much less than the denser regions. Gravity helps make the voids larger in a relative sense, because matter near their edges is drawn toward the surrounding filaments and clusters. Over time, the contrast grows. The dense regions become denser, and the voids become more sparse. This does not mean that matter is pushed away by gravity. It means that the pull from denser surroundings removes matter from regions that began with less mass. The emptiness of a void is therefore also a gravitational result. Along the filaments, gravity creates a slow inward traffic. Matter tends to move from less dense regions toward more dense ones, and then toward the knots where several filaments meet. These knots become galaxy clusters, the most massive bound structures in the universe. A cluster can contain hundreds or thousands of galaxies, along with hot gas and dark matter. Yet the cluster is not separate from the filament. It is part of the same connected pattern, a dense crossing point in the wider network. The terrifying quality of gravity at this scale does not come from sudden violence, but from persistence. It allows no true isolation. Every mass contributes to the shape of the field around it, and every other mass responds. Across millions of light years, the effect is weak at any given moment, yet time gives it consequence. Slight imbalances grow. Small motions become large separations. Quiet regions are drained. Dense regions deepen. The web is a record of gravity's patience. The expansion of the universe continues through this region as well. On the greatest scales, distant parts of the web separate as space expands. Within denser parts, gravity holds matter together or slows its separation. The web therefore exists in a balance between local attraction and cosmic expansion. Filaments and clusters are shaped by attraction, while the larger background continues to stretch. Observations indicate that this balance has changed over cosmic time as the expansion of the universe has evolved. It remains uncertain how all components of the universe, including dark energy, fit into a complete physical description, but their combined effects are measured through the growth of structure. In this region, gravity also stores memory. A filament's present shape reflects conditions from the early universe, the later motion of matter, and the continuing pull of surrounding structures. The arrangement is not designed, and it is not still. It is a slow result of physical law acting through time. Matter follows the paths available to it, and gravity shapes those paths through the presence of mass and energy. At the scale of the galactic web, gravity is no longer only the force that makes objects fall or keeps planets in orbit. It becomes the reason the universe has large-scale form. It gives matter a tendency to gather, and that gathering produces the pattern within which galaxies live. The web surrounds each galaxy with a larger history, placing it inside filaments, near voids, or within clusters. Every smaller system is embedded in this broader architecture, and every smaller motion inherits part of its direction from the wider field. The region remains calm in appearance because the distances are enormous and the changes are slow, yet beneath that calm, gravity continues to reshape the distribution of matter. It pulls gas into filaments, draws galaxies toward clusters, bends light, deepens dense regions, and leaves voids increasingly open. It acts through the whole network without interruption. The web is therefore not merely a map of where galaxies happen to be. It is the visible trace of gravity turning tiny early differences into the vast structure of the universe. Around the Milky Way, gravity forms a wide enclosure that reaches far beyond the bright band of stars visible from within the galaxy. This region is known as the halo, a broad and diffuse volume surrounding the galactic disk. It contains old stars, globular clusters, thin gas, and a much larger amount of unseen matter inferred from motion. The halo does not glow with the same richness as the disk, yet it holds much of the galaxy's gravitational importance. Observations indicate that stars and gas in the Milky Way move as if the galaxy contains far more mass than can be counted through visible stars alone. This unseen mass is described as dark matter, meaning matter that does not emit, absorb, or reflect enough light to be directly detected, but still produces gravity. In this outer galactic region, gravity is measured through motion. Stars near the visible edge of the Milky Way orbit the galactic center at speeds that cannot be explained by the visible matter alone. If only the bright disk and central bulge supplied the pull, those outer stars would move more slowly. Instead, their speeds remain high, indicating that an extended halo contributes additional gravity. This finding is part of a broader pattern seen in many spiral galaxies. It remains uncertain what dark matter is made of, but its gravitational influence is consistently observed through the motions of stars, gas, and galaxies. The halo is not a sharp shell. It thins gradually into the space around the galaxy. Its outer boundary is difficult to define, because gravity has no clean edge where it suddenly stops. The Milky Way's pull weakens with distance, but it continues to influence smaller galaxies nearby. Some dwarf galaxies move around the Milky Way as satellites, held by the combined gravity of the visible galaxy and its dark halo. Their paths are long and slow, shaped by the mass they orbit and by interactions with one another. Some of these small galaxies show signs of being stretched by tidal forces, which are differences in gravitational pull across an object. The nearer side of a satellite galaxy is pulled more strongly than the farther side, and over time this difference can draw out streams of stars. These stellar streams are quiet evidence of gravity's reach. They form when a small galaxy or star cluster is gradually pulled apart as it travels through the Milky Way's halo. Stars that once belonged to a single bound system become spread along a common path, tracing the orbit of the disrupted object. The stream may be faint, but it preserves information about the gravitational field through which it moves. By mapping these streams, astronomers can study the shape and distribution of the Milky Way's halo. Observations indicate that the halo is not perfectly simple or smooth, and it may carry signs of past mergers with smaller galaxies. The halo also contains globular clusters, dense groups of old stars bound tightly by their own gravity, while orbiting within the larger pull of the Milky Way. These clusters can contain hundreds of thousands of stars packed into nearly spherical shapes. Their ages indicate that they formed early in the history of the galaxy or were acquired through mergers. As they move through the halo, they act as tracers of the galaxy's mass. Their orbits are guided by the gravitational field that surrounds them, and their positions help reveal how the galaxy is built beyond its bright disk. In this region, gravity keeps a record of the Milky Way's history. The galaxy has not always been a single settled form. It grows by drawing in smaller systems, absorbing gas, stars, and dark matter from its surroundings. Some of this material becomes part of the disk or central regions, while some remains in the halo as streams, clusters, or scattered stars. The halo is therefore not only a container but also an archive of past encounters. Its faint structures show that gravity does not merely bind matter, it also dismantles and redistributes it. The pull of the halo affects the disk from outside. The stars and gas of the visible Milky Way rotate within the broader gravitational field created by all the galaxy's mass. This field helps determine orbital speeds and long-term stability. Without the extended halo, the motion of the outer disk would not match what is observed. The galaxy's bright shape is therefore only the inner, luminous part of a larger gravitational system. The visible Milky Way rests inside a wider mass distribution that cannot be seen directly. Gravity in the halo has a quiet but unsettling scale. It surrounds the familiar galaxy with a vast unseen structure. The Sun and nearby stars are not moving only through a bright disk of visible matter. They are also embedded in the deeper pull of a halo whose contents remain partly unknown. This does not imply chaos or danger in any immediate sense. It means that the motions of stars depend on a mass distribution that observation can measure through effects, but cannot yet fully identify in substance. The halo's influence reaches toward neighbouring systems as well. The Milky Way and the Andromeda Galaxy are moving within the gravity of their local group, a collection of galaxies bound together on a scale smaller than the cosmic web but larger than any single galaxy. The Milky Way's halo is part of this local gravitational environment. Nearby dwarf galaxies, streams, and intergalactic gas all respond to overlapping pulls. The boundaries between one galaxy's influence and another's are gradual, defined by motion rather than by a visible line. Within the halo, gravity is slow enough to seem almost still, yet strong enough to shape the fate of entire systems. A dwarf galaxy can orbit for billions of years before being stripped. A stream can stretch across the sky while remaining faint to the eye. A cluster can circle the galaxy many times while preserving its dense center. These motions are not separate events. They are expressions of one continuous gravitational field. Extending outward from the Milky Way and blending into the wider environment, at this distance from the galactic center, gravity shows one of its most important truths. What is visible is not always what dominates motion. The bright stars give the galaxy its image, but the unseen halo gives much of its mass. The paths of stars, clusters, and satellite galaxies reveal a structure larger and deeper than light alone suggests. In the Milky Way's halo, gravity becomes a way of knowing what cannot yet be seen, and the galaxy becomes not just a shining disk, but a vast hidden enclosure held together by an invisible pull. Inside the wide halo, the Milky Way becomes brighter and more defined. Its galactic disk spreads outward as a broad, flattened system of stars, gas, and dust, all turning around the center in long curved paths. This region contains the luminous body of the galaxy, where spiral arms wind through the disk and where much of the visible matter gathers. Gravity gives this disk its shape, not as a rigid structure, but as a moving balance, Every star follows its own orbit. Every cloud of gas drifts under shared attraction, and every region of dust responds to the combined pull of the whole galaxy. The disk is thin compared with its width. Its stars are not arranged in a flat sheet, but they remain concentrated close to a central plane because gravity pulls material toward that plane over time. Gas clouds settle even more strongly into the disk, where collisions and pressure remove some of their random motion. Stars, once formed, can move above and below the plane, but the overall system remains flattened because its motion carries angular momentum, a measure of turning motion. The galaxy does not simply collapse inward, because matter in the disk is also moving sideways around the center. Gravity pulls inward, while orbital motion carries material forward, producing curved paths rather than a direct fall. This balance can be seen in the rotation of the galaxy. Stars near the Sun travel around the galactic center at hundreds of kilometers per second, though their motion appears calm from within the system because the distances are so large. A full orbit takes hundreds of millions of years. The stars do not feel a solid track beneath them. They follow the shape of the gravitational field created by the galaxy's visible matter and its extended dark matter halo. Their paths are steady in broad outline, yet not perfectly circular, because the disk contains spiral arms, gas clouds, star clusters, and other uneven concentrations of mass. Spiral arms are not fixed objects made of the same stars forever. They are patterns in the disk, regions where gas and stars become more crowded for a time. Gravity helps maintain these patterns by guiding matter into denser lanes, while rotation carries stars and gas through them. Gas clouds entering a spiral arm may become compressed, and this compression can support the formation of new stars. The bright young stars then make the arms more visible. The pattern remains, even as individual stars move through it and continue along their orbits. Gravity also acts between smaller parts of the disk. A giant molecular cloud, which is a cold and dense cloud of gas where molecules can form, has its own gravity. If parts of the cloud become dense enough, they can contract further. Pressure, turbulence, magnetic fields, and heat can resist collapse, so the process is not simple or uniform. Still, gravity provides the inward tendency that allows stars to form. Within the disk, star formation is therefore another expression of gravity, working on scales much smaller than the galaxy, but still tied to the larger galactic environment. Dust lanes mark some of the places where gas is concentrated. Dust grains are tiny solid particles mixed with gas, and they can block or redden starlight. Their presence reveals that the disk is not empty between stars. It contains a thin interstellar medium, a mixture of gas, dust, radiation, and magnetic fields. Gravity shapes this medium by drawing material into clouds and by keeping much of it within the galactic plane. At the same time, energy from stars can stir the gas, heat it, and drive some of it away from dense regions. The disk remains a balance between inward gathering and outward stirring. The Sun is part of this disk, but it is not located at the center. It lies in a quieter region between major spiral features, orbiting with nearby stars in the same broad rotation. From this position, the Milky Way appears as a pale band across the sky, because the view looks through the thickness of the disk, where many distant stars blend into a soft glow. That band is not a separate object. It is the inside view of the galactic plane. Gravity holds the stars in that plane statistically, giving the sky its broad luminous stripe. In the disk, gravity can be steady and disruptive at the same time. It keeps stars bound to the galaxy, but it also creates encounters. Passing stars can slightly change one another's motions. Dense clouds can tug on nearby stars. Spiral patterns can shift orbits over long periods. These effects are usually gentle for individual stars, yet they accumulate across time. The disk is not a machine with perfectly repeating paths. It is a living gravitational system, always adjusting as its parts move and interact. Open star clusters form in the disk when many stars are born from the same cloud. Their shared gravity may hold them together for a time, but encounters with gas clouds and the general pull of the galaxy gradually loosen them. Many clusters disperse, and their stars become part of the wider disk population. This dispersal shows that gravity can bind and unbind depending on scale and circumstance. A cluster may be stable for millions of years, then slowly lose its shape under the larger gravitational field through which it travels. The disk also contains the effect of vertical gravity. Stars and gas above or below the plane are pulled back toward it. They pass through the plane and move outward again, oscillating around it over long times. This motion gives the disk thickness. The thickness depends on the speeds of the stars and the strength of the restoring pull. Older stars often have more varied motions and can form a thicker component, while younger stars and gas remain closer to the plane. Gravity thus sorts the disk by motion and age, leaving a layered structure without a sharp boundary. There is no need for gravity in the disk to announce itself through dramatic collapse. Its normal state is continuous guidance. It keeps the galaxy rotating, gathers gas into arms, holds stars near the plane, bends orbits around the center, and slowly changes the arrangement of matter. The terrifying part is again not sudden destruction, but the absence of escape from relation. Every star belongs to the field of the whole. Every cloud is shaped by nearby mass and by the galaxy's total pull. Even emptier regions of the disk are not free from gravity, because the field extends through them invisibly. Within the galactic disk, gravity becomes familiar in form but still immense in reach. It gives the Milky Way its visible body, its spiral structure, its flattened shape, and much of its motion. The disk glows because stars shine, but the stars shine within paths that gravity has made possible. The whole region is a moving compromise between fall and forward motion, between gathering and stirring, between local clouds and the larger galaxy. From the inside, it appears peaceful. Yet its calm is the calm of constant motion held in balance by a force that never stops acting. Within the galactic disk, the region around the Sun appears less crowded than the dense spiral arms and less empty than the spaces far above the plane. This local region is part of the Milky Way's broad rotation, but it has its own nearby pattern of stars, gas, dust, and motion. Gravity here becomes easier to imagine because the distances are smaller than the span of the whole galaxy. Yet the scale remains far larger than any planet or ordinary human measure. Nearby stars move through the same general gravitational field, each following a path around the galactic center, while also responding faintly to the pull of other stars and clouds in the neighborhood. The Sun travels with many surrounding stars, but it is not fixed among them. Each nearby star has its own speed and direction. Some drift closer over long periods, and others move away. These changes are slow, taking thousands or millions of years to alter the local sky. Gravity influences these motions through the combined mass of the galaxy, but close stellar encounters can also make small adjustments. A passing star does not need to collide with another star to have an effect. Stars are so widely separated that direct collisions in this region are extremely unlikely, yet their gravity can still alter paths by a small amount when they pass near one another. This local drift shows that gravity does not require contact. A star can influence another star across great distances through the shape of the gravitational field around it. In ordinary terms, the field is the way space around mass carries information about attraction. A star moving through the local neighborhood is therefore not alone, even when it appears isolated. It is part of a shared environment where every object contributes something to the motion of others. Most effects are small because distances are large, but over long time spans, small effects become part of the history of motion. Between the stars, the interstellar medium remains thin but important. It includes gas made mostly of hydrogen and helium, with traces of heavier elements and dust. Some regions are warmer and more diffuse, while others are cooler and denser. The Sun is moving through a relatively low-density area near the edge of small local clouds. Gravity helps shape these clouds, though pressure, heat, turbulence, and magnetic fields are also important. In a diffuse cloud, gravity may be too weak to cause collapse. In a denser cloud, gravity can become more important, especially when material gathers enough mass in one region. The local interstellar environment has been shaped by earlier generations of stars. Massive stars can end their lives by exploding as supernovae, spreading gas and heavier elements into the surrounding space. Such events can carve out low-density cavities and push material into shells and clouds. Gravity later acts on this disturbed material, guiding it into new arrangements. The local region is therefore not only a place of present motion, but also a record of past heating, expansion, and settling. Gravity works within that record, not alone, but always as the tendency for mass to gather and influence other mass. Open clusters sometimes pass through the broader solar neighborhood, and some nearby stars were likely born in clusters that have since dispersed. When a group of stars forms together, their shared gravity can hold them for a time. But the pull of the Milky Way, encounters with gas clouds, and the different speeds of individual stars gradually spread many clusters apart. Once dispersed, their stars continue on related but separated paths. Astronomers can identify some of these moving groups by measuring position, speed, and chemical composition. Their common motion points back to a shared origin, while gravity explains both their early binding and their later loosening. The Sun itself is a single star in this local flow. Its gravity dominates only within a limited region around it, where planets, smaller bodies, and dust remain bound to the solar system. Beyond that region, the Milky Way's gravity and the motions of other stars become more important. There is no solid boundary where the Sun's influence ends completely. Instead, its pull weakens with distance until other influences shape motion more strongly. This gradual fading is a central feature of gravity. It extends without a clean edge, but its importance depends on what other masses are nearby and how fast objects are moving. Nearby stars also carry their own small systems. Some have planets, debris disks, or clouds of small bodies. Each system is held together locally by the gravity of its star, yet each system also travels through the galaxy. The result is a layered pattern. A planet orbits a star. The star orbits the galactic center, and the local group of neighboring stars shifts gradually as the disk rotates. Gravity binds these layers without making them rigid. They move together for a time, but not forever in the same arrangement. In the solar neighborhood, gravity appears less dramatic than in clusters of galaxies or the crowded center of the Milky Way. The stars are sparse, and the space between them is vast, yet the same law is present. It bends paths, maintains orbits, disperses clusters, shapes clouds, and connects the local region to the larger disk. The quietness can be misleading. A star passing within a few light years may make only a slight change to distant small bodies around the Sun, but across enough time, such encounters can alter the outer edges of a planetary system. The effect is not constant danger. It is a reminder that even a calm neighborhood is not isolated from the gravitational movement of the galaxy. Measurements from space observatories allow astronomers to map this region with increasing precision. The positions and motions of many stars reveal that the local neighborhood is not still. It streams, ripples, and rotates as part of the galactic disk. Some patterns may come from spiral structure, past encounters, or waves moving through the disk. Observations indicate that the local motion is more complex than a simple circular orbit. It remains uncertain how every small pattern formed, but the broad cause remains gravity acting through a disk filled with stars, gas, and dark matter. This region shows gravity as a local environment rather than a distant cosmic principle. It is the reason nearby stars do not simply scatter without relation. It is also the reason their relations constantly change. No star keeps the same neighbors forever. Over long spans, the Sun moves through different surroundings, passing clouds, meeting different stellar neighborhoods, and carrying its own bound system through the larger galactic field. The calm of the local region is therefore a slow passage through a changing gravitational landscape, where every motion is both individual and shared. At the outer edge of the solar system, the Sun's gravity becomes faint but still meaningful. This region is far from the bright central warmth of the Sun, beyond the familiar paths of the major planets, where small icy bodies move through cold and dim space. The Sun remains the main source of attraction, but its pull is weaker here than in the inner solar system. Objects travel slowly, and their orbits can be stretched, tilted, or disturbed by the gravity of passing stars, the wider Milky Way, and the large planets farther inward. The region does not end with a wall. It thins outward through layers of smaller bodies whose paths reveal how far the Sun's influence can reach. The Kuiper Belt occupies part of this distant region. It is a broad zone of icy bodies beyond the orbit of Neptune. Some of these bodies are small and irregular, while others are large enough to be nearly round under their own gravity. Pluto is one member of this distant population. The objects in this belt are remnants of the early solar system, preserved in cold conditions where change is slow. Gravity gives their motion order, keeping many of them in stable orbits around the Sun, while Neptune's gravity shapes their paths in more specific ways. Some bodies move in orbital rhythms with Neptune, meaning their periods around the Sun form stable repeating relationships. These relationships help prevent close encounters and allow the bodies to remain in place over long spans of time. Gravity in this region shows itself through restraint rather than speed. The farther an object orbits from the Sun, the longer it takes to complete one path. A body in the Kuiper Belt may need hundreds of years to circle the Sun. Its motion is slow because the Sun's pull is weak at that distance, and the orbit is wide. Still, the object is not drifting freely into interstellar space. It remains bound because its motion and the Sun's attraction form a stable curve. The same principle applies to a planet, but here the curve is wider, colder, and more easily disturbed. Beyond the Kuiper Belt, the solar system becomes more diffuse. Scattered objects follow elongated paths that may carry them from the outer planetary region to much greater distances. These orbits often show the influence of past encounters with Neptune or other gravitational disturbances. A small body passing near a giant planet can have its orbit change strongly, not because the planet touches it, but because the planet's gravity redirects its motion. The body may be sent inward, outward, or into a more tilted path. Gravity here acts like a quiet exchange of motion, with large bodies altering the routes of smaller ones. Farther still lies the region associated with long-period comets, often described through the idea of the Oort cloud. This is thought to be a vast, distant reservoir of icy bodies surrounding the Sun at distances far beyond the planets. It has not been directly observed as a whole, because its bodies are small, dark, and extremely distant. Its existence is inferred from the path of comets that enter the inner solar system from many directions. Observations indicate that such comets likely come from a distant, roughly spherical population. It remains uncertain exactly how many objects it contains and how its outer boundary is shaped. In this distant cloud, the Sun's gravity is very weak, yet it can still bind objects over enormous times. The motion of these bodies is slow and delicate. A small outside influence can matter. The gravity of nearby passing stars can shift their orbits. The gravitational field of the Milky Way can also exert a slow tidal effect, changing the paths of distant comets over long periods. A comet that has remained far from the Sun for billions of years can be nudged into a path that carries it inward. When it later approaches the warmer inner regions, ice can turn into gas and dust, creating a visible coma and tail. The bright event begins with a faint gravitational change in a dark outer region. The Sun's outer influence is therefore not absolute. It overlaps with the larger galaxy. In the inner solar system, the Sun's gravity dominates so strongly that galactic tides are negligible for planetary motion. At the farthest reaches, the balance changes. The Sun still binds many objects, but the Milky Way and passing stars can reshape the weakest orbits. The solar system's edge is not a simple border. It is a transition where local gravity gradually gives way to the wider gravitational environment of the galaxy. The large planets also leave a deep imprint on this outer region. Jupiter, Saturn, Uranus, and Neptune are much smaller than the Sun, yet their gravity can strongly affect small bodies that pass near them. Neptune shapes the Kuiper belt. Jupiter can redirect comets that enter the planetary region. Some small bodies become trapped in temporary or long-lasting orbits, while others are thrown outward or inward. Gravity does not only hold objects in place, it can scatter them, protect them, or remove them from a system. The outer solar system carries signs of this long history of scattering. Many distant bodies preserve clues from the solar system's formation. Their icy composition suggests that they formed in cold regions, or were moved there early in the system's history. Gravity gathered dust and ice into larger objects, while the growing planets rearranged many of their paths. Some bodies remained in belts, some were scattered outward, some were lost from the solar system entirely. The present outer region is the result of that early movement, followed by long, quiet intervals in which weak gravity continues to guide distant motion. This region can feel unsettling because it shows that even the Sun's rule is limited. The star that holds the planets also has an outer reach that becomes fragile. Far from the Sun, small objects remain bound only loosely, and their paths can be altered by events that pass almost unnoticed across interstellar distances. A star moving through the wider neighborhood may never come close to the planets, yet its gravity can disturb remote icy bodies. The galaxy itself can gently bend the farthest orbits. The solar system is not a sealed chamber. It is a gravitational system immersed in a larger one. At the outer edge, gravity is nearly silent. There are no bright surfaces, no dense atmospheres, and little sunlight. There are only small bodies moving slowly through darkness, held by a pull that is weak but persistent. Their existence shows that gravity does not need strength in the ordinary sense to matter. It needs distance, motion, and time. In this remote region, the sun's attraction becomes a thin thread extending into the dark, still able to bind, still able to shape, and still open to the wider pull of the galaxy. Inside the distant edge of the solar system, the planets follow paths that make gravity appear more orderly and more familiar. Each planet moves around the sun in a curved orbit, neither flying away into space nor falling directly into the star. This balance comes from two parts of motion working together. The sun's gravity pulls inward, and the planet's forward motion carries it sideways. The result is an orbit, a continuous fall that keeps missing the central body. This description is simple, but it holds a deep truth. Gravity does not need to push or guide from a surface. It shapes motion through the presence of mass, turning straight paths into curves. The planets do not move in perfect circles. Their orbits are ellipses, which are slightly stretched circles with the sun near one focus. For most major planets, the stretching is modest, so their paths appear nearly circular when seen from a distance. Their speeds change along these paths. A planet moves a little faster when it is closer to the sun, and a little slower when it is farther away. This pattern follows from the way gravity and motion conserve energy and angular momentum. Angular momentum is the measure of turning motion, and in an orbit it helps keep the planet from simply falling inward. The inner planets move quickly because they are close to the sun and feel a stronger pull. Mercury completes an orbit in less than 1 Earth year, while Earth takes 1 year and the outer planets take much longer. Neptune needs many human lifetimes to complete one path around the sun. This difference is not accidental. The farther a planet is from the sun, the weaker the sun's pull becomes, and the longer the path around the sun becomes. Gravity sets both the curve and the pace. The planets also pull on one another. The sun dominates the system because it contains nearly all of the solar system's mass, but the planets are not massless. Jupiter, the largest planet, has the strongest planetary influence. Its gravity slightly shifts the paths of other bodies and helps shape the motion of asteroids and comets. Saturn, Uranus, Neptune, and the smaller planets contribute as well. These influences create small departures from simple two-body motion. A planet's orbit is therefore not an isolated line, but part of a shared gravitational arrangement. These interactions can remain stable over very long periods. The planets have moved in their present broad arrangement for billions of years, though not without small changes. Their orbits shift slowly in orientation and shape because of the combined pull of the other planets. These gradual changes are called perturbations, meaning small gravitational changes from a simple path. Perturbations can be measured and predicted with high accuracy over many timescales, over extremely long times. However, the full system becomes more difficult to predict in exact detail, because small differences can grow. Observations and calculations indicate that the major planets remain stable on timescales far longer than human history, but exact positions in the very distant future become uncertain. Gravity also explains why planets are nearly round. A planet has enough mass for its own gravity to pull its material inward from all directions. Rock, metal, ice, and gas settle toward a shape close to a sphere, because a sphere places the surface as evenly as possible around the center. Rotation can flatten a planet slightly at the poles and widen it at the equator, especially for large, fast-spinning gas giants. Still, the basic roundness comes from gravity, overcoming the strength of material on planetary scales. Smaller asteroids can remain irregular because their gravity is too weak to smooth their shapes completely. Around planets, moons follow the same principle that planets follow around the sun. A moon is pulled inward by its planet while moving forward along a curved path. Earth's moon remains bound to Earth, and many other planets hold moons of their own. Some moons are large enough to be round, some are small and irregular. Their orbits reveal the mass of the planets they circle. By measuring how a moon moves, scientists can determine the strength of the planet's gravity and estimate its mass. Gravity becomes a tool for weighing worlds without touching them. Tides are another sign of orbital gravity. A tide is caused by the difference in gravitational pull across a body. The moon pulls more strongly on the near side of Earth than on the far side, and the sun contributes a smaller but important effect. This difference raises ocean tides and also flexes solid Earth slightly. Tides are not only an ocean feature, they occur in moons, planets, stars, and even galaxies whenever gravity acts unevenly across an extended body. In the planetary region, tidal forces can heat the interiors of moons, slow rotations, and gradually change orbits. The planets also occupy a system shaped by past gravity. During formation, dust and gas circled the young sun in a rotating disk. Particles collided and stuck together. Larger bodies gathered more material, and growing planets cleared or scattered nearby objects. Gravity made small differences matter. A slightly larger body attracted more material and grew faster. Over time, this process produced planets, moons, asteroids, and leftover debris. The present orbits are therefore not only paths through space, they are the surviving arrangement from an ancient period of gathering, collision, and scattering. In the planetary region, gravity can seem peaceful because the motion is regular. Sunrise, seasons, eclipses, and planetary positions follow patterns that can be predicted. Yet the same order reveals the power of a force that never pauses. The Earth does not stay near the Sun because space is still. It stays near the Sun because it is continuously falling around it. The Moon does not hang in the sky. It is always curving around Earth. A satellite remains above the planet only because its forward speed and Earth's pull are precisely related. Without that motion, gravity would bring it downward. Without gravity, motion would carry it away. This region makes the terrifying nature of gravity quiet and exact. It is not terrifying because the planets are unstable in any immediate way. It is unsettling because stability itself depends on constant falling. Every orbit is a state of being held, not at rest, but in motion. Nothing in the planetary system is simply placed. Every body is moving through a gravitational field, and its future path depends on mass, speed, distance, and the pull of all the others. The Sun's gravity binds the planets into a coherent system, but it does not freeze them. It allows motion, cycles, seasons, tides, and long-term changes. It gives each world a path and gives the system a structure. In this region, gravity becomes both the cause of order and the reminder that order is dynamic. The planets trace their paths in silence, held by an invisible relation that turns falling into orbit and motion into a lasting architecture. Near Earth, gravity becomes immediate, measurable, and familiar, yet it remains the same force that shapes galaxies and planets. This region begins above the atmosphere, where spacecraft, satellites, small debris, and the Moon all move within Earth's gravitational influence. Earth's pull is much stronger here than it is in distant interplanetary space, because distance from Earth's center is smaller. Objects near the planet are drawn downward with enough strength that remaining above the surface requires motion. A satellite in orbit does not escape gravity. It stays in orbit because it moves forward fast enough that its fall follows the curve of Earth. Low Earth orbit lies only a few hundred kilometers above the surface. close enough that Earth fills much of the view from a spacecraft. At this height, gravity is only slightly weaker than it is on the ground. The feeling of weightlessness inside an orbiting spacecraft does not mean gravity has vanished. It means the spacecraft and everything inside it are falling together. The floor no longer presses upward in the usual way, so objects float. Their floating is a state of shared free fall, not a release from Earth's pull. Satellites at different heights move at different speeds. A lower satellite must travel faster to remain in orbit because Earth's gravity is stronger there and the curve of the orbit is tighter. A higher satellite moves more slowly and takes longer to circle the planet. Some satellites are placed in an orbit where their period matches Earth's rotation. From the ground, such a satellite can appear to remain above the same region. This does not mean it is fixed in space. It is moving around Earth in step with the planet's turning, held in a careful balance between forward motion and inward pull. Gravity near Earth is not perfectly even. Earth is not a perfect sphere, and its mass is not distributed with complete uniformity. Mountains, ocean trenches, dense rock formations, and the planet's equatorial bulge all make small changes in the gravitational field. These changes are tiny compared with the whole pull of Earth, but they can be measured. Satellites that map gravity detect subtle variations, revealing information about ice sheets, groundwater, ocean movement, and the structure of the planet beneath the surface. Gravity therefore becomes a way of sensing hidden mass. The Moon occupies the outer part of this near-Earth gravitational region. It orbits Earth because Earth's gravity pulls it inward, while its forward motion carries it along a curved path. The Moon also pulls on Earth. This mutual attraction is important. Earth and the Moon both move around a shared centre of mass, which lies inside Earth but not exactly at Earth's centre. The system is therefore not one body fixed and another moving around it. It is a pair of bodies responding to each other's gravity, with Earth's greater mass keeping the shared motion close to itself. Tides show this connection clearly. The Moon's gravity pulls more strongly on the side of Earth facing the Moon, and less strongly on the far side. This difference produces tidal bulges in the oceans and smaller tides in the solid body of Earth. The Sun also contributes to tides, though the Moon's effect is stronger for Earth's oceans because it is much closer. When the Sun, Earth, and Moon align, tidal ranges tend to be larger when their pulls act at right angles. Tidal ranges tend to be smaller. These cycles are regular, but local coastlines, seafloor shapes, and ocean depths make real tides complex. Tidal gravity also changes the Moon's motion over long time spans. The interaction between Earth's rotation and ocean tides transfers angular momentum from Earth to the Moon's orbit. As a result, the Moon slowly moves farther from Earth, while Earth's rotation very gradually slows. The change is small in human terms, measured over long intervals, but it shows that gravity can exchange motion between bodies without contact. The Earth-Moon system is not frozen. It evolves through the steady action of tides. Objects near Earth can also fall from orbit if their paths are altered. In low orbit, traces of atmosphere remain even at heights that seem like space. These thin particles create drag, slowly removing orbital energy from satellites and debris. As an orbit lowers, atmospheric drag increases, and the object may re-enter the denser air. Gravity pulls it downward throughout the process, while air resistance converts motion into heat. The return to Earth is not caused by gravity suddenly beginning to act. Gravity has been acting the entire time. The orbit ends because forward motion is reduced. The same principle explains falling objects near the surface. A stone released from rest accelerates downward because Earth's gravity changes its motion. Air resistance can slow the fall, especially for light or broad objects, but gravity supplies the inward pull. In a vacuum, objects fall with the same acceleration regardless of their mass, as long as other forces are absent. This fact shows that gravity affects motion in a way that is not simply proportional to heaviness in the everyday sense. A larger object has more gravitational force on it, but it also has more resistance to acceleration, so the two effects balance. Near Earth, gravity also gives weight. Weight is the force felt when the ground, a floor, or a seat prevents an object from following its natural fall. A person standing on Earth is not motionless in a deeper physical sense. Earth's gravity pulls inward and the ground pushes upward. The sensation of weight comes from that upward support. Remove the support and falling begins. In orbit, support is absent because spacecraft and contents fall together. On the ground, support is constant because the surface blocks the inward path. This near-Earth region makes gravity seem ordinary because it governs daily experience. It holds air close to the planet, keeps oceans on the surface, guides satellites, shapes tides, and gives bodies weight. Yet its ordinary presence is also what makes it severe. It acts on every object at every moment. It does not need to be noticed in order to function. It holds the moon in a path around Earth and pulls loose stones toward the ground through the same underlying influence. There is no sharp divide between falling, orbiting, and being held up by the surface. They are different outcomes of motion under gravity. A falling object lacks enough sideways speed to miss Earth. An orbiting object has enough sideways speed to keep missing Earth. A resting object is prevented from falling by the material strength of the ground. In this region, gravity reveals its quiet exactness. It is the reason space near Earth is not empty freedom, but a layered field of paths, falls, supports, tides, and motions, all curved around the mass of the planet. Within Earth's atmosphere and oceans, gravity becomes a constant downward tendency that shapes layers of air and water. This region is dense compared with space, filled with molecules that collide, mix, and respond to temperature and motion. Gravity acts on every particle, pulling it toward the center of the planet. Because of this pull, the atmosphere does not spread evenly into space. Instead, it becomes thicker near the surface and thinner with height. Air pressure, which is the force per area from the weight of air above, decreases steadily as altitude increases. The lower atmosphere supports the weight of all the air above it, while higher layers support less. This vertical structure forms because gravity gives direction to the movement of gas. Molecules in the atmosphere are in constant motion due to heat. They move in all directions, colliding with one another and with surfaces. Without gravity, this motion would spread gas evenly in all directions over time. With gravity, upward motion is gradually balanced by the downward pull. Some molecules move upward with enough speed to reach higher altitudes, but many lose energy through collisions and return downward. The result is a layered atmosphere, where density and pressure are highest near the ground and decrease with height. Temperature also affects this structure. Warm air tends to expand and become less dense, while cooler air becomes denser. Gravity interacts with these differences. Less dense air can rise above denser air, creating vertical movement known as convection. Convection allows heat to move through the atmosphere, carrying energy from the surface upward. At the same time, gravity ensures that rising air does not escape entirely. It eventually cools, slows, and may sink again. This cycle creates weather patterns winds, and cloud formation. The motion appears dynamic, yet gravity provides the steady downward reference that organizes it. Water in the oceans responds to gravity in a similar way. The ocean surface settles into a shape determined by Earth's gravitational field and its rotation. This shape is not perfectly smooth, but it is close to an equipotential surface, meaning a surface where gravitational and rotational effects balance so that water does not flow across it in a steady state. Waves, currents, and tides disturb this surface, yet gravity pulls water back toward an overall level. When a wave rises, gravity acts to bring it down again, converting the motion into oscillation rather than escape. Pressure in the ocean increases with depth because of the weight of water above. Each layer of water supports the weight of all layers above it. This leads to very high pressure in deep regions, where the weight of kilometers of water presses downward. The increase in pressure affects the behavior of water, the structure of materials, and the life that can exist at different depths. Gravity therefore sets not only the shape of the ocean, but also the physical conditions within it. Tides continue to influence the oceans in this region. The gravitational pull of the moon and the sun creates periodic changes in sea level. These changes move through ocean basins as waves of long wavelength, interacting with coastlines and seafloor features. Gravity governs both the creation of tides and the restoring force that brings water back toward equilibrium. The combined effect produces a steady rhythm of rising and falling water, modulated by local geography and ocean dynamics. Rivers and precipitation also reflect gravity's influence. Water in the atmosphere condenses into droplets when conditions allow, forming clouds. When droplets grow large enough, they fall as rain, snow, or other forms of precipitation. Gravity draws this water downward to the surface, where it collects in streams, rivers, and lakes. From higher elevations, water flows toward lower elevations, following paths shaped by terrain. Over time, this flow erodes rock, transports sediment, and reshapes landscapes. Gravity thus connects the movement of water in the air with the shaping of land. The atmosphere and oceans are not static layers. They are in constant motion due to energy from the sun, Earth's rotation, and internal processes. Gravity interacts with all of these influences. It provides the force that keeps gases bound to the planet, the reason liquids form surfaces, and the cause of pressure gradients that drive motion. Without gravity, there would be no stable atmosphere, no oceans resting on the surface, and no sustained weather systems as they are known. The terrifying aspect of gravity in this region lies in its absolute presence. Every breath depends on air being held close to Earth. Every drop of water remains part of the ocean because gravity prevents it from drifting away. At the same time, gravity ensures that anything unsupported will fall. A cliff, a falling object, or a landslide all follow the same rule. The atmosphere cushions motion with resistance, but gravity sets the direction and provides the continuous pull. In this region, gravity becomes both a stabilizing and a limiting force. It allows complex systems such as weather, climate, and ocean circulation to exist, yet it also defines boundaries. Air cannot remain indefinitely at high altitude without energy input. Water cannot remain suspended without support. Particles settle, layers form, and differences in density lead to movement. Gravity organizes matter into vertical structures, giving the planet a sense of up and down that shapes every process within these layers. The connection between atmosphere and ocean also depends on gravity. Evaporation lifts water vapor into the air, but the vapor remains part of the atmosphere because gravity holds it. Condensation returns it to liquid form, and gravity brings it back to the surface. This cycle links sky and sea through continuous motion. The energy driving the cycle comes largely from the sun, but gravity ensures that the cycle remains bound to Earth. In this layer of the planet, gravity is no longer distant or abstract. It is immediate, shaping pressure, density, flow, and stability. It defines the vertical dimension of the environment, creating a world where fluids settle, move, and return. The air above and the water below are held in place by a force that does not vary in direction, only in strength with distance. It acts quietly and continuously, giving structure to the most familiar parts of the planet while remaining as fundamental as in the farthest reaches of space. On Earth's surface, gravity shapes the solid landscape in ways that unfold slowly but persistently. Mountains rise through internal forces, yet their forms are constantly adjusted by the downward pull that acts on every grain of rock. No structure stands without limit. Gravity draws material toward lower elevations, and over time this motion reshapes even the highest terrain. The surface becomes a record of balance between forces that build upward and gravity that brings material down. Rocks at the surface experience stress due to their own weight and the weight of layers above. When slopes become steep, gravity can overcome the strength of the material holding them together. This leads to landslides, rock falls, and the gradual movement of soil known as creep. Creep is slow, often unnoticed over short periods, but it continuously shifts material downhill. Tiny movements accumulate, and slopes change shape. Trees may lean slightly as the ground beneath them moves, and structures can tilt over time if the soil is unstable. Gravity does not require sudden failure to act. It works through steady pressure as well as abrupt motion. Water enhances the effect of gravity on land. Rainfall seeps into soil and rock, adding weight and reducing friction between particles. Saturated ground can become unstable, making slopes more likely to fail. Rivers, driven by gravity, carve channels through the landscape, carrying sediment from higher regions to lower ones. Over long periods, river systems can cut deep valleys, shaping entire regions. The motion of water is guided by the same principle seen in smaller scales. It flows downhill because gravity pulls it toward lower elevations, and its path is determined by the terrain it encounters. Glaciers provide another example of gravity acting on solid material. A glacier is a mass of ice that forms when snow accumulates and compresses over time. Under its own weight, the ice begins to flow slowly downhill. The movement is not like a liquid, but it behaves in a way that allows it to deform and slide. Gravity drives this motion, causing glaciers to carve valleys, transport rocks, and leave behind distinct landforms. Even though the movement is slow, the scale of a glacier allows it to reshape landscapes over thousands of years. The concept of weight becomes evident in this region. Every object resting on the ground exerts a force downward due to gravity. The ground provides an equal upward support, preventing motion. This balance allows structures to stand, but it also places limits on what materials can support. Tall buildings require strong foundations because gravity pulls on every part of the structure. The design of such structures must account for the distribution of weight, ensuring that forces are directed safely into the ground. Without sufficient support, gravity would cause collapse. Mountains themselves reveal gravity's influence through their height. There is a limit to how tall a mountain can become, determined by the strength of the rock and the pressure at its base. As a mountain grows taller, the weight of the rock increases the pressure on lower layers. At some point, The rock may begin to deform or fail under this pressure. This does not mean mountains stop forming, but it means their growth is balanced by processes that reduce their height, including erosion and internal deformation. Gravity ensures that no surface structure can grow without limit. Erosion is a continuous expression of gravity. Wind can move particles through the air, but gravity brings them back to the ground. Water can carry sediment across long distances, but its motion follows the pull toward lower elevations. Over time, sharp features become smoother, and steep slopes become gentler. The landscape evolves toward forms that are more stable under gravity. This process does not remove all variation, but it moderates extremes. Volcanic activity also interacts with gravity. When molten rock reaches the surface, it flows outward and downward, guided by the shape of the land. Lava can build new landforms, yet gravity shapes their final appearance. Ash and debris ejected into the air eventually fall back to the ground, adding layers to the surface. Even explosive events, driven by internal pressure, end with material settling under gravity's pull. The distribution of mass within Earth's crust affects local gravity slightly. Dense rock formations exert a stronger pull than less dense materials. These variations are small but measurable, and they can be used to study the structure beneath the surface. Gravity surveys help identify features such as mineral deposits, voids, and changes in rock type. The surface landscape therefore reflects not only visible processes, but also the hidden distribution of mass below. Gravity also governs the behavior of loose materials. Sand, soil, and gravel tend to settle into shapes that reflect the angle at which they can remain stable. This angle depends on the properties of the material, such as grain size and moisture content. When the slope exceeds this angle, the material moves downhill until a stable configuration is reached. This simple rule shapes dunes, slopes, and piles of debris. It shows how gravity interacts with material properties to determine form. On the surface, gravity is constant and unavoidable. It acts on everything at all times, shaping motion, stability, and change. The terrifying aspect is not sudden destruction alone, but the certainty that all elevated material is subject to eventual movement. A cliff may stand for long periods, yet its form is temporary in the face of gravity and erosion. A mountain may rise through tectonic forces, yet it will be worn down over time. The landscape is never fixed. It is always adjusting under the influence of gravity. This region reveals gravity as a force that defines the boundary between structure and collapse. It allows forms to exist, yet it continuously tests their stability. Every rock, every slope, and every surface feature exists within limits set by gravity. These limits do not prevent change, they ensure it. The ground beneath any structure carries the weight of what stands upon it, and the balance must be maintained. In the crust and mountains, gravity becomes a visible sculptor. It shapes valleys, guides rivers, limits heights, and drives the slow movement of material. Its action is patient and relentless, transforming landscapes over spans of time that extend far beyond human experience. The solid surface of Earth, often seen as stable, is in fact part of a continuous process governed by a force that never rests. Beneath the crust, Earth's mantle forms a vast region of hot rock under pressure. It extends from the base of the crust to the outer boundary of the core, making up most of the planet's volume. This region is solid in the ordinary sense, but over very long spans of time it can deform and flow. Gravity acts through the mantle as weight, pressure, and motion. Every layer presses on the layers below it, and the deeper the rock lies, the greater the pressure becomes. The mantle is therefore not simply a hidden mass beneath the surface. It is a deep gravitational environment where rock behaves differently because it carries the weight of the planet above. At shallow mantle depths, rock is already under pressure far greater than at the surface. Minerals are squeezed into stable forms that can endure heat and compression. Temperature rises with depth, but pressure also rises, and pressure can keep rock solid even when it is extremely hot. This balance matters because the mantle is not mostly liquid. It is a solid that moves slowly by creeping, a process in which material deforms under long-lasting stress. Gravity helps drive this motion by making denser material tend to sink and less dense material tend to rise. Convection in the mantle is the slow movement of hot and cooler material caused by differences in density. Heat from Earth's interior warms some regions, making them slightly less dense. Under gravity, this less dense material can rise slowly. Cooler material near the upper mantle becomes denser and can sink. The motion is very slow, usually measured over geological time, but it is powerful because the mantle is enormous. This deep circulation helps move heat outward and contributes to the motion of tectonic plates above. Gravity does not create the heat, but it gives density differences a direction and turns them into movement. The sinking of cold slabs is one of the clearest examples of gravity's role in the mantle. At some plate boundaries, oceanic lithosphere, which includes crust and the uppermost rigid mantle, bends downward and descends into the mantle. This process is called subduction. The descending slab is cooler and denser than the surrounding mantle, so gravity helps pull it downward. The motion can influence earthquakes, volcanic arcs, and the recycling of surface material into Earth's interior. Once a slab begins to sink, its own weight can become a major driving force in plate motion. As material descends, pressure changes the minerals within it. Some minerals transform into denser structures, allowing atoms to pack more tightly. These phase changes occur at certain depths, where pressure and temperature conditions favor new forms. A phase change is a transformation in material structure without changing the basic chemical composition. In the mantle, such changes affect density, strength, and the way seismic waves travel, seismic waves, which are vibrations from earthquakes and other sources, reveal these boundaries because they speed up, slow down, or change direction as they pass through different materials. Gravity compresses the mantle not only downward but inward from all directions toward Earth's center. The pressure at depth is produced by the weight of overlying rock and by the planet's spherical shape. A piece of mantle rock deep inside Earth is pressed by material above and around it. This pressure changes how minerals behave and how easily rock can deform. Near the surface, rock may break. Deep in the mantle, under heat and pressure, rock is more likely to bend and flow slowly. Gravity helps create the conditions that make this deep behavior possible. The mantle's movement is not a simple circular flow, it is complex, uneven, and influenced by temperature, composition, mineral changes, and the arrangement of tectonic plates. Some regions may rise as broad plumes of hot material, some regions sink as cold slabs. Some motion is layered, while other motion crosses depth boundaries. Observations indicate that mantle flow exists and affects the surface, but the exact pattern inside Earth remains partly uncertain because it must be inferred from seismic imaging, laboratory experiments, gravity measurements, and computer models. This uncertainty does not weaken the central role of gravity. The mantle moves because differences in density become meaningful under a gravitational field. A dense slab can sink only because there is a downward direction. A buoyant plume can rise only because surrounding denser material tends to move downward in comparison. Pressure increases with depth because gravity gives weight to the overlying rock. Even heat transfer is shaped by gravity once density differences appear. Without gravity, the mantle would not have the same layered pressure, the same slow overturning, or the same connection to surface tectonics. The mantle also helps balance the crust through a process called isostasy. Isostasy is the tendency of Earth's outer layers to float in gravitational balance on the deeper, slowly deforming mantle. Thick mountain roots extend downward into the mantle, while thinner oceanic crust sits lower. When ice sheets grow, their weight depresses the crust. When they melt, the crust can slowly rebound as mantle material adjusts. This process shows that the solid Earth has a kind of deep, slow response to changing loads. Gravity supplies the load, and mantle flow allows adjustment. In this hidden region, the terrifying nature of gravity is expressed through pressure and time. At the surface, gravity may feel like weight on the body or the fall of an object. In the mantle, it becomes the weight of continents, oceans, mountains, and all overlying rock. It presses minerals into new forms, drives dense slabs downward, supports slow planetary circulation, and keeps the whole interior under compression. There is no empty space where this pressure is absent. Every depth carries the burden of the mass above. The mantle is often imagined as still because it is solid and unseen. In reality, it is a region of slow motion. Its flow is too slow to watch directly, but it shapes the surface through plate movement, uplift, subsidence, and volcanism. Gravity is present in every part of this motion, not as a sudden pull, but as a constant condition. It gives the mantle its pressure structure and allows differences in heat and density to become geological change. Within the mantle, gravity is no longer only an external force acting on landscapes. It is part of the planet's internal architecture. It compresses, sorts, and moves material through deep time. The surface rests above this region, but it is not separate from it. Mountains, basins, volcanoes, and plate boundaries are linked to the mantle's slow response under gravity. The deeper the path moves, the more gravity appears as inward weight, shaping matter not by visible falling, but by pressure, density, and the long, silent motion of rock. At the center of Earth, gravity reaches a different expression, no longer seen as motion across a surface or flow through layers, but as compression gathered from all directions. The core is divided into two main parts, an outer core of liquid metal and an inner core that is solid. Both are composed mostly of iron, with smaller amounts of other elements. The distinction between liquid and solid here is not set by temperature alone. It is set by the balance between temperature and pressure, and gravity is the source of the immense pressure that defines this region. As depth increases, the weight of all overlying material presses inward. At the boundary between the mantle and the core, pressure is already extremely high. Deeper still, the pressure rises further, reaching values that can only be understood through indirect measurement and theoretical models. Observations indicate that seismic waves, which travel through Earth during earthquakes, behave differently when passing through the core. Some waves slow down or stop in the liquid outer core, while others pass through the solid inner core with changes in speed. These behaviors reveal the state of matter under extreme conditions. The outer core is fluid because its temperature is high enough to overcome the tendency of atoms to lock into a fixed structure, even under great pressure. In this liquid metal region, gravity still acts by pulling material inward, but the fluid can move in response to heat and rotation. This motion contributes to the generation of Earth's magnetic field through a process known as the geodynamo. The details of this process involve complex interactions between fluid motion, electrical conductivity, and rotation. It remains uncertain exactly how all aspects of the geodynamo operate, but it is clear that the movement of liquid metal in the outer core is essential. The inner core, by contrast, is solid. This may seem counterintuitive because it is hotter than the outer core, yet it remains solid because the pressure is even greater. Gravity compresses the iron atoms so strongly that they are forced into a fixed arrangement despite the heat. This shows that gravity can influence the state of matter in a fundamental way. Temperature tends to increase atomic motion, while pressure tends to restrict it. In the inner core, pressure dominates. The center of Earth is a point where gravitational forces from all directions balance. At that exact center, there is no net pull in any direction, because mass surrounds it equally. Yet the pressure there is the result of all the mass above pressing inward. This combination of balanced force and extreme pressure illustrates a subtle aspect of gravity. It can create intense conditions even where directional pull cancels out. The core is therefore not a place of falling in the usual sense, but a place of accumulated weight. Gravity also shapes the growth of the inner core. Over time, as Earth cools, some of the liquid metal in the outer core solidifies onto the inner core. This process releases heat and contributes to the motion in the outer core. The inner core may slowly increase in size as this solidification continues. Observations indicate that the inner core has a radius of several thousand kilometers, though its exact growth rate and detailed structure remain uncertain. Its surface is not like a solid boundary an ordinary experience. It is a transition between phases under extreme conditions. The core's density is higher than that of the mantle and crust above it. This distribution of density is a result of gravity acting during Earth's formation. When the planet was young and hotter, materials separated according to density. Heavier elements, especially iron and nickel, moved inward under gravity, forming the core. Lighter materials remained in the outer layers. This process, called differentiation, shows how gravity sorts matter on a planetary scale, the present structure of Earth. With a dense core and lighter outer layers, reflects this early sorting. Pressure in the core affects not only the state of matter, but also the way waves travel through it. Seismic waves provide one of the main ways to study the core, because direct sampling is not possible. By observing how these waves change speed and direction, scientists infer the properties of the materials they pass through. These observations indicate that the outer core does not support certain types of waves, confirming its liquid nature, while the inner core supports them, confirming its solidity. The interpretation of these signals depends on understanding how gravity shapes pressure and density at depth. The terrifying aspect of gravity in the core lies in its absolute dominance. At the surface, gravity can be resisted by structures or balanced by motion. In the core, there is no such balance in the everyday sense. Every part of the material is under compression from all sides. There is no empty space, no relief from pressure, and no simple way for material to move except through slow, constrained processes. The weight of the entire planet presses inward, and that pressure defines the environment completely. Despite these extreme conditions, the core is not inactive. The liquid outer core moves, the inner core grows slowly, and the entire region interacts with the mantle above through heat flow and gravitational coupling. The rotation of Earth also affects the core, introducing additional forces that shape fluid motion. Gravity remains central to all of these processes providing the inward pull that creates pressure and influences density differences. The core is hidden from direct view, yet its effects reach outward. The magnetic field generated by the outer core extends far into space, protecting Earth from charged particles and shaping the near-Earth environment. The structure of the core influences how heat moves through the planet, affecting mantle convection and, indirectly, surface geology. Gravity connects these layers, ensuring that the conditions at the center are linked to the behavior of the whole planet. In this deepest region, gravity is no longer experienced as a simple pull downward. It becomes the reason matter is compressed, the cause of phase changes, and the force that shaped Earth's internal structure from the beginning. It is present in the weight of every layer above, in the motion of liquid metal, and in the solid state of the inner core. The center of Earth is therefore not just a distant point. It is the focus of a continuous inward pull that has gathered the planet into its present form and continues to define its internal state. Inside ordinary matter, gravity becomes extremely faint compared with the forces that hold atoms and molecules together. This region is not inward in space like the layers of Earth, but inward in scale. The path now reaches the small structures from which rocks, oceans, air, bodies, and stars are made. At this level, matter is built from atoms, and atoms are held together mainly by electromagnetic forces. Electromagnetism is the force associated with electric charge, light, and magnetic effects. It binds electrons to atomic nuclei and allows atoms to form molecules, solids, liquids, and gases. Gravity is still present, but its influence between individual particles is extraordinarily weak. An atom consists of a small dense nucleus surrounded by electrons. The nucleus contains protons and neutrons, which are themselves made from smaller particles. The attraction between an electron and the positively charged nucleus is electromagnetic, not gravitational. The gravitational pull between them is so small that it has no meaningful effect on the structure of the atom. If gravity were the only force available at this scale, atoms as known would not form. The shapes, sizes, and chemical behavior of atoms are governed by quantum mechanics and electromagnetism, not by ordinary gravitational attraction. Within the nucleus, gravity is even less important. Protons have positive electric charge, and like charges repel one another through electromagnetism. Yet protons and neutrons remain bound inside nuclei because of the strong nuclear force. The strong nuclear force is a short-range force that holds the particles in atomic nuclei together. It is far stronger than gravity at this scale, though it acts only over extremely small distances. This force allows nuclei to exist despite electric repulsion among protons. Gravity contributes so little that it can usually be ignored in calculations of nuclear structure. This faintness of gravity at small scales is one of the deepest contrasts in nature. Gravity governs planets, stars, galaxies, and the structure of the universe. Yet between two particles it is far weaker than the other fundamental forces. Its power comes not from strength at the particle level, but from accumulation. Electric charges can be positive or negative, and their effects often cancel in large collections of matter. Ordinary objects contain nearly equal amounts of positive and negative charge, so their electromagnetic influence at a distance can become small. Gravity, however, has no known negative mass that cancels ordinary mass in the same way. Every bit of mass and energy contributes attraction. Because of this, gravity grows important when enormous amounts of matter gather. In a stone resting on the ground, atoms are held in place by electromagnetic bonds. The stone has weight because Earth's gravity pulls on its mass, but the stone does not collapse through the ground because electromagnetic forces between atoms resist compression. The surface pushes back through the interactions of electrons and nuclei. What feels like solid support is, at small scale, the result of electromagnetic resistance. Gravity pulls the stone downward, but electromagnetism gives matter its stiffness and shape. The ordinary world is therefore a balance between gravity acting on mass and other forces giving matter structure. In liquids, gravity shapes the bulk motion while molecular forces shape the material itself. Water forms droplets and surfaces because of electromagnetic interactions among molecules. Gravity pulls the water downward, making it settle into containers, rivers, lakes, and oceans. A small droplet can remain rounded because surface tension, an electromagnetic effect between molecules at the surface, can dominate over gravity when the droplet is tiny. A large body of water, by contrast, is shaped mainly by gravity because its mass is large enough for weight to overwhelm surface tension. Scale decides which force becomes visible. Dust grains show the same transition. A tiny grain can cling to a surface through electromagnetic effects that are stronger than its weight. Fine powder can behave in ways that seem to resist simple falling because small forces between grains matter. Yet a landslide or a collapsing cliff is governed by gravity because the total mass involved is large. The small-scale forces still determine friction, cohesion, and material strength, but gravity supplies the downward drive. This is why the same force can be nearly irrelevant between two atoms and dominant in a mountain. Inside living bodies, gravity is also present but not the main force at the microscopic level. Cells, proteins, membranes, and fluids are organized by chemical bonds, pressure differences, and thermal motion. Gravity affects the body as a whole by giving weight and direction, influencing circulation, posture, balance, and growth. But the molecules inside cells do not arrange themselves because of their mutual gravity. They respond to chemistry, charge, heat, and molecular shape. The body stands in gravity, but life's small machinery is built mainly from electromagnetic and quantum interactions. The weakness of gravity at small scales makes it difficult to fit into the same framework as the other forces. Quantum mechanics describes the behavior of matter and energy at atomic and subatomic scales. General relativity describes gravity as the curvature of space-time caused by mass and energy. Both theories are strongly supported in their own domains, yet they use different mathematical foundations. It remains uncertain how gravity should be described at the smallest scales, where quantum effects cannot be ignored. This uncertainty becomes especially important in extreme environments, but even in ordinary matter, it marks a boundary in understanding. Gravity's faintness also explains why experiments seeking its quantum behavior are so difficult. The gravitational effect of a small object is tiny, easily overwhelmed by electromagnetic forces, vibration, heat, and other influences. Measuring gravity between small masses requires great isolation and precision. Observations confirm gravity across many scales, but its behavior at the smallest quantum level remains one of the unresolved areas of physics. The known facts do not suggest that gravity vanishes there. They show that its influence is usually hidden beneath stronger effects. At this inner scale, gravity becomes terrifying in a different way. It is not strong enough to build atoms, yet it cannot be removed from the universe. It is almost absent in the structure of a molecule, then becomes unavoidable when enough molecules gather into a planet. It is the weakest familiar pull between small things, but it becomes the architect of stars and galaxies because it adds without cancellation. Its quietness at the small scale is not failure, it is patience. It waits for mass to accumulate. Ordinary matter therefore contains a layered truth. The hardness of rock, the flow of water, the shape of a cell, and the chemistry of air come from forces much stronger than gravity at small distances. Yet all of this matter has weight when gathered near Earth, orbits when placed in space, and collapses when assembled into stars. Gravity does not explain the internal structure of atoms, but it explains what collections of atoms do when they become large enough, in the small region of matter. Gravity is nearly silent, but its silence is only local. The same atoms that ignore one another gravitationally can, in vast numbers, bend the paths of planets, hold atmospheres, and curve light across the universe. At a deeper level of description, gravity is no longer treated as a simple force acting across space, but as a property of spacetime itself. Spacetime is the combined framework of space and time, where positions and events are defined together. In this view, mass and energy do not pull objects in the traditional sense. Instead, they change the geometry of spacetime, and objects move along paths determined by that geometry. This idea comes from general relativity, a theory that has been tested in many ways and agrees closely with observation across a wide range of conditions. In curved spacetime, the path of an object is called a geodesic. A geodesic is the natural path that an object follows when no other forces act on it. In flat spacetime, a geodesic is a straight line. In curved spacetime, a geodesic appears as a curved path when viewed from ordinary space. A planet orbiting the Sun is following such a path. It is not being pulled sideways by an invisible thread, it is moving forward through spacetime, and the curvature around the Sun causes its path to bend into an orbit. This description replaces the idea of a force acting at a distance with the idea of motion within a shaped geometry. Mass and energy determine how spacetime curves. A more massive object creates a stronger curvature. This curvature affects not only matter, but also light. Light always follows the straightest possible path in spacetime, but when spacetime is curved, that path appears bent. This is why light passing near a massive object, such as a galaxy cluster or the Sun, is deflected. Observations of this bending match the predictions of general relativity. The effect is small near Earth, but becomes more pronounced near very massive or dense objects. Time is also affected by gravity in this framework. Clocks in stronger gravitational fields run more slowly compared with clocks in weaker fields. This effect is known as gravitational time dilation. It has been measured using precise clocks at different altitudes on Earth and in orbit. The difference is small in everyday situations, but it becomes significant in strong gravitational environments. This shows that gravity is not only about motion through space, it also affects the passage of time. The curvature of spacetime can be described mathematically by equations that relate mass, energy, and geometry. These equations are complex, but their meaning is clear in principle. Matter tells spacetime how to curve, and spacetime tells matter how to move. This relationship removes the need for a force acting across empty space. Instead, the presence of mass changes the structure of spacetime itself, and objects respond by following the paths available within that structure. In weak gravitational fields, such as near Earth or in the solar system, the predictions of general relativity closely match those of the simpler description of gravity as a force. This is why the older model remains useful for many calculations. In stronger fields, such as near very massive stars or black holes, the differences become important. the curvature can become so strong that paths of light and matter change dramatically, and time behaves in ways that are far from everyday experience. Gravitational waves are another consequence of this geometric view. When massive objects accelerate, especially in systems like merging black holes or neutron stars, they can create ripples in spacetime. These ripples travel outward at the speed of light, carrying energy away from the system. Observations have confirmed the existence of these waves, providing direct evidence that spacetime itself can be disturbed and that gravity can propagate as a wave. The detection of these waves requires extremely sensitive instruments because the effects are very small by the time they reach Earth. Despite its success, general relativity is not complete. It describes gravity well on large scales and in strong fields, but it does not fully integrate with quantum mechanics, which governs the behavior of matter at the smallest scales. Attempts to create a unified theory of quantum gravity remain an active area of research. Observations indicate that general relativity works extremely well in known situations, but it remains uncertain how it should be modified or extended at the smallest scales or at the earliest moments of the universe. The terrifying aspect of gravity in this description lies in its fundamental nature. It is not something that can be shielded or turned off. It is woven into the structure of space-time itself. Every object with mass or energy contributes to the curvature, and every object moves within that curved structure. There is no separate background that remains unaffected. The stage and the actors are part of the same system. This perspective also changes the meaning of falling. An object in free fall is not being pulled in the usual sense. It is following a natural path through curved space-time. The sensation of weight arises when something prevents that motion, such as the ground supporting a person. In orbit, where objects follow geodesics, there is no sensation of weight because nothing resists the motion. This interpretation unifies falling, orbiting, and weight within a single concept. Space-time curvature is usually gentle in everyday conditions. The Earth curves space-time slightly, enough to guide the motion of satellites and falling objects. The Sun creates a stronger curvature, shaping planetary orbits. Only in extreme environments does the curvature become intense. Yet even in mild conditions, the principle is the same. The familiar experience of gravity is a local expression of a deeper geometric property. In this region of understanding, gravity is no longer just an interaction between masses. It is a feature of the universe's structure. Space and time are not fixed backgrounds. They respond to mass and energy, and in doing so, they determine how motion unfolds. The quiet, steady pull experienced on Earth is one aspect of a more general phenomenon that operates across all scales. The shift from force to geometry does not remove gravity's influence. It deepens it. It suggests that every motion, every orbit, and every fall is guided by the shape of space-time. The universe is not simply filled with objects that attract one another. It is shaped in such a way that motion follows certain paths, and those paths are determined by the distribution of mass and energy. This view reveals gravity as something embedded in the fabric of reality, not separate from it. At the deepest limits of current understanding, gravity enters regions where known descriptions begin to lose clarity. Black holes and the smallest scales of space-time represent environments where the familiar picture of gravity as smooth curvature meets conditions that are not yet fully explained. Observations indicate that general relativity describes black holes with high accuracy at distances outside their central regions. It predicts that when enough mass is compressed into a small volume, space-time becomes so strongly curved that not even light can escape beyond a boundary known as the event horizon. This boundary marks a point of no return for information and matter that pass within it. A black hole does not act like an object with a surface in the ordinary sense. Its defining feature is the way it shapes space-time around it. Outside the event horizon, objects can orbit, light can bend, and time passes in a way that depends on distance from the center. Closer to the event horizon, time for an outside observer appears to slow for anything approaching it. Light emitted from near the boundary becomes increasingly redshifted, meaning its wavelength stretches as it climbs out of the gravitational field. These effects have been observed indirectly in systems where black holes interact with surrounding matter, and in the motion of stars near the center of galaxies. Inside the event horizon, the known equations of general relativity lead to a prediction of continued collapse toward a region of extremely high density, often described as a singularity. A singularity is a point where quantities such as density and curvature would become infinite in the mathematical description. It remains uncertain whether this description reflects a physical reality or indicates a limit of the theory. Many physicists expect that a more complete theory, combining gravity with quantum principles, would describe this region differently. At present, there is no confirmed description that fully replaces the singularity in a way consistent with all observations. Black holes also reveal that gravity can affect information and radiation in subtle ways. Quantum theory suggests that black holes are not completely black. They can emit a form of radiation due to quantum effects near the event horizon, often called Hawking radiation. This radiation arises from the behavior of quantum fields in curved spacetime. Over extremely long periods, it could lead to the gradual loss of mass from a black hole. Observations have not yet directly confirmed this radiation because it is very weak for known black holes, but the theoretical prediction is widely studied. It remains uncertain how information about matter that falls into a black hole is preserved or transformed in this process. At the smallest scales, the nature of space-time itself becomes uncertain. Quantum mechanics suggests that at very small distances and times, physical quantities can fluctuate. Applying this idea to space-time implies that the smooth geometry described by general relativity may not hold at all scales. Instead, space-time might have a more complex or discrete structure. Several theoretical approaches attempt to describe this regime, including models where space-time is made of fundamental units, or where additional dimensions exist. None of these ideas has yet been confirmed by direct observation. The difficulty in combining gravity with quantum mechanics arises because the two frameworks describe reality in different ways. General relativity treats space-time as a continuous geometric entity influenced by mass and energy. Quantum mechanics describes particles and fields using probabilities and discrete interactions. When gravity becomes strong at very small scales, such as near a singularity or during the earliest moments of the universe, both descriptions are needed, but they do not yet fit together in a single consistent theory. This gap marks one of the central open questions in physics. Observations of the early universe also point to limits of current understanding. The expansion of the universe suggests that it was once in a much denser and hotter state. Extrapolating backward using general relativity leads to conditions where density and temperature become extremely high. As with black holes, this leads to a point where known equations may no longer apply. It remains uncertain what description replaces them at that stage. Some models suggest a beginning with different properties, while others suggest a transition from a prior state. Current observations constrain these ideas but do not yet select a single complete explanation. Gravity in these extreme conditions reveals its most unsettling aspect. It governs the structure of space-time on large scales and shapes the motion of matter and light. Yet it also leads to situations where current theories cannot fully describe what happens. The same force that explains planetary motion and galactic structure leads to questions about the nature of time, information, and the smallest building blocks of reality. It is both well understood and incomplete. The persistence of gravity across all scales adds to this tension. It does not fade away where theories become uncertain. It remains present, influencing every process even where description fails. In a black hole, gravity determines the boundary from which nothing escapes. In the early universe, gravity shapes the overall expansion and structure. At the smallest scales, it must exist alongside quantum effects, even if the exact relationship is not yet known. This region also suggests that gravity is connected to deeper principles that have not yet been fully uncovered. The behavior of black holes, the possibility of quantum fluctuations in space-time, and the structure of the early universe all hint at a more fundamental framework. Observations continue to test the limits of current theories, and new measurements refine the understanding of where those limits lie. The process is ongoing, guided by data from telescopes, detectors, and experiments. In the innermost sense, gravity becomes a question as much as a description. It is known to shape the universe from the largest structures to the smallest scales that can be tested, yet its complete nature remains partially hidden. The terrifying quality is not only its strength or reach, but its depth. It is embedded in the structure of reality, and it leads to conditions where known laws approach their limits. At this final inward step, gravity is no longer just a force or a curvature that can be mapped and predicted. It is a doorway into unanswered questions about space, time, matter, and the origin of the universe. It binds galaxies, guides planets, shapes landscapes, compresses cores, and fades into near silence within atoms. Yet it re-emerges at the boundaries of knowledge. The journey from the outermost cosmic structures to this inner uncertainty reveals a single continuous influence that is both familiar and unresolved, constant and incomplete, present in every layer and still not fully understood. The motion slows, and the sense of scale softens into a quiet continuity. Gravity remains present without effort, a steady relation between mass, space, and time. It shapes without noise, holding patterns in place while allowing them to change. The vast structures of the universe, the turning of galaxies, the quiet orbit of a planet, and the stillness of a resting stone all follow from the same underlying condition. Nothing is separate from it, yet nothing feels its full extent at once. The mind settles into the idea that falling, orbiting, and resting are not different states but variations of motion within a single field. The weight of the body, the flow of air, the calm surface of water, and the slow drift of stars all share a common origin. Gravity does not hurry. It does not need to. Time allows it to shape everything gently, steadily, without interruption. The thought of unseen mass, curved space-time, and distant horizons fades into a simpler awareness. Objects remain where they are because motion and gravity are in balance. The ground supports, the air rests above it, and the sky extends without boundary. The pull toward the center is constant, yet it is also the reason for stability. The quiet continues, with no need for change or effort. Gravity holds each part of the world in relation to the rest. The same influence extends outward beyond sight and inward beyond direct knowledge, linking every scale without separation. The mind can rest within this continuity, where motion is guided and nothing drifts without relation, the universe remains in slow, steady order, shaped by a force that is always present and never hurried.